All right, this is curve fitting 2. So there are two things I'd like to mention in this video. The first thing is we can fit things other than functions. So let me give you an example, and I'll make a comment about what the criteria is as we go. It's a criteria we've seen, but I just want to sort of give you an example. So consider these points. Suppose you encounter these 4 points. So we'll have 0, 5. We'll have, say, 1, negative 5, 4, 0, and say negative 4, negative 1. So clearly they don't fit, they probably don't fit a function. But maybe we think, well, maybe they fit a circle centered at the origin, or possibly maybe an ellipse centered at the origin. So we suggest, and again, don't worry about where these suggestions come from other than sort of a little bit of intuition. Perhaps these are close to an ellipse. Centered at the origin. So then we say, well, okay, what does an ellipse centered at the origin look like, right? So such an ellipse has the equation ax squared plus by squared equals 1. Right? And you could put a constant on the right hand side instead of a 1, but then you can just divide it away. So every single ellipse at the origin will have this form. And a and b will be positive. Otherwise, we might get a hyperbola, but we don't need to worry about that here, right? So for our points to satisfy this, all right, this is what we get. We have to plug them in and get a value, right? So let's put them in order. So we'll do 0, 5 is the first one that I listed. We'll just go maybe counterclockwise or clockwise, for example. So 0, 5. We get a times 0 squared plus b times 5 squared equals 1. 4, 0. We're going clockwise here. We'll get a times 4 squared plus b times 0 squared equals 1. 1, negative 5. A times 1 squared plus b times negative 5 squared equals 1. And negative 4, negative 1. A times negative 4 squared plus b times negative 1 squared equals 1. So this can be simplified a little bit so we can see that it's linear. I'm going to leave the zeros in as coefficients because it should be an A, because it'll help us when we write down the matrix. And so noticing these first two equations, that it looks like we could solve for A and B, but the point is that we're suggesting that we can't actually find A and B. So we have this system. So this system then as a matrix looks like this. Should be a 1 here just to be precise. Times AB equals 1, 1, 1, 1. No solution here. You can probably see that by looking at if A and B had solutions, they would, if the first two equations give us A and B, those won't fit in the last two equations. So we can find the least squares solution. So again, using what we know, if we consider this, I used the letter A already. Let me say M for this one. And this is B bar. So just a reminder, we get the solution A, B hat, because they're not real A, B. So this will be M transpose M inverse M transpose B. So when we get this, we get this approximately from MATLAB. These two values. So this suggests our ellipse will be 0.0612 x squared plus 0.0388 y squared equals 1. Now, if we plot this, we can find the intercepts. So we can find those, of course, by setting x and y equal to 0. So if we set y equal to 0, again, these are approximate values. We get 4.040. This is plus or minus. Let's be really clear. That's when y equals 0. And when x equals 0, we get plus or minus 5.080. So if we plot these with our points, so we've got a point at 0, 5. This is at 5, 4, 0. 1, negative 5, and negative 4, negative 1. And so this particular circle, or rather ellipse, this extends to, in the x direction, a little bit more than 4. So like maybe just a smidge, barely out to the right. And a little bit more than 5. So it's sort of like this. It's missing everything, but it's so close. Now, just as a final comment for this particular example, which I put down here, is because we're not matching a function, right? When we matched a function, our function was of the form y equals. And so as a consequence, we were minimizing the y distance. Here we're not, right? Here it's a little more obscure because what's happening is we're taking the ellipse, we're plugging it in, and we're getting 1. Or rather, when we're plugging in, if we were to go back and plug our points in to the ellipse that we got, we wouldn't get 1 and we wanted to. So what we're actually sort of minimizing is the sum of the squares of the differences of what we get when we plug in our points and 1, right? So, but the practical upshot is this is not minimizing the sum of squares of y differences, because we're not modeling, or we're not fitting y equals. Right? So in terms of what it is visually minimizing is a little more complex. So I'm not going to worry about that overly much, but just wanted to point out, in this case, we get something close, but it's not exactly perfect. Or it's not exactly minimizing the same thing we had before. So the last thing I want to mention is just a comment about choosing functions. So this is more of sort of a data analysis comment. So let me clear the screen and then we'll just make a few quick comments. We'll give an example and then we'll look at some possibilities. So we'll say to choosing functions. So the point being, given a bunch of points, picking, let's say, a reasonable function. It's sort of part art, part science, as is data analysis, right? So if you don't know which approaches to take, choosing an approach can be sort of either a qualitative or a quantitative thing, right? So there are no exact rules. There could be lots of possibilities. We'll say lots of possibilities arise. So take a look at a simple example. So consider these points. Again, I'm pulling this straight out of the book, so you can see some pretty graphs there. But I just want to sort of talk through what happened in there. And I'm not going to show overly many calculations. Again, those are all in the book. This is just to sort of give you an idea what's happening. So if you plot these, you get something like the point says 1 at the almost at the origin. There's 1 slightly above it. It looks like it's at the origin because the y values get so high, so the scale is a bit messed up. So you look at this and you don't know what it fits, right? So for what it's worth, data doesn't fit necessarily functions, right? All you're asking when you do data analysis is what's the best possible model, right? So you look at this and you might say, well, maybe it's exponential. Maybe it's parabolic. What you're really saying is which model is best. You're not really saying, people will say, is the data exponential or parabolic, or quadratic if you prefer the term to parabolic. But really what's going on is that's not the question. The question is which model is best. So what you can do is you can sort of just try some. You go like maybe exponential. So exponential, for example, doesn't need to be base e, right? So maybe you think it looks like this. For some ABC. The problem is if you plug your points in, this is not linear, right? So because of the, and you can try this, and I suggest that you try this, is when you plug in your x's and your y's, that product BC ends up such that you cannot write down a matrix equation. All right, so for example, just so that you see, when you plug in the first, or let's say the second point, 2, 5. If you plug this in, you get 5 equals a plus b times c to the 2. And there's no, like this will not fit if you try to put this in. Right, doesn't work. So maybe you say to yourself, well, that the C is kind of awkward. Like, could we guess at a C? This might get it out of the way, right? So then you might say, well, for example, I know that 15, 150, right? So I look at that point, and this is where the part science comes in, right? So maybe I say to myself, well, it goes up near 15, 150. So maybe, perhaps, you might say like, well, you might look at an exponential like c to the x equals y to test. And then you say like, well, when I put in 15, I want to get about 150. So maybe you get this and you get 1.3966. So maybe try C equals 1.4. All right, so there's a little hacking going on here, right? We're sort of saying, look, forget the A for a second and forget the B. Let's just look at the C to the X equals Y. All right, so what happened here, just so we're clear, is I did this. This is just to test, right? Simplify to play, and we said, well, look, if it fit that and it goes through this point, the point 15, 150, that might give us a C. Again, it's not perfect. You could well have said, well, what about 1375? And so we're just sort of playing with ideas here, right? So if this is the case, then what we're going to go with is y equals a plus b times 1.4 to the x. You can do least squares on this. Right, so I'm going to skip the intermediate steps, but it's the same as before. We plug in the 5 points, we get a matrix equation. We can't solve it for a and b, so we do least squares for a and b. And when we do this, yeah, we can write y equals, we can just cut to the chase. We get this, 1.8982 plus 0.9463, 1.4 to the x. So this was on maybe exponential. Well, then maybe you say maybe quadratic. This is for some ABC. So if we do this, again, there's least squares going on in here. Let's just be really, really clear about this. Let me just make sure I label things. So what's happening here is this is least squares to here. And then this is going to be least squares to here. All right. So in other words, what we get when we do this is we get y equals 1.3577 x squared plus minus 11.7172x plus 10.9079. Now, interestingly, you can compare them. So the exponential least squares error compared to the quadratic least squares error. So the quadratic is 21.9904. The exponential is 2.7601. So arguably this one's a little better. Of course, it may not be best, right? Like we had a C of 1.4 in our exponential, but that came from the 15 and 150. So maybe you could find a different C, like 1.3 or 1.5, or use a different pointer. Start with an intercept. There are lots of options, right? The options abound. And so when you look at this, I don't want you to look at this and think that when you do this as a specific procedure to follow, right? The quadratic, this was the easiest one. The quadratic had no issues. It was you get a matrix, everything works nicely. The exponential we needed to play around, and there are lots of different ways to play around. So there's actually one more thing I wanted to do. I thought there were just two, but let me clear the screen and just mention the last thing. Really easy. So 3 is just a note on predicting. And all I want to end with is saying, once we've got a function or equation or whatever, we can then use it to predict values. So for example, in the previous example, I'm just going to go off of this one. If you went with the quadratic, all right, so if in the previous question we had gone with this, right? So we might suggest then, right? We found the exponential one was better, but for the sake of argument, let's suppose we went with this. So then you can predict, for example, and we could suggest, for example, that when x is 10, when x is 20, which is a value we didn't have, that I was going to say f of 20, but we'll just say y is 1.3577 times 20 squared minus 11.7172 times 20 plus 10.9079. So this is approximately 319.6439. So we've sort of extrapolated or interpolated, really, because it's in the middle of the data, but we've predicted a new value. So this is where the strength of these models come from. They come from, building the model from the data that's there, figuring out how good the model is using least squares. And then when you think you've got a pretty good one, you use it to predict some other data. So that's the last thing I want to mention. That's the end of the two videos. So let me finish that up. Done.